Hey guys, welcome to my channel. And if you have seen some other videos of mine, you would know that I discuss questions on statistics. But today I'm going to start a new topic, which is optimization. And the book I'm going to refer to is Mathematics for Economic Analysis. This book was written by Knut Sydsaeter and Peter J. Hammond, right? So the chapters that are mainly that deal with optimization are chapter 17 and chapter 18. Chapter 17 is multivariable optimization and chapter 18 is constrained optimization. Now, if you don't have any basic knowledge of optimization, then you should go and try to read the book or watch some other video on YouTube. But what I am going to do is I am going to solve almost each and every question of this book from all of the exercises, so that after trying the example on your own or getting some basics correct from some other channel or reading the book again and again, if you come up to the questions and you deal with some problem in those questions, then coming on this channel and seeing the solutions will help you a lot, right? So let's just start. Let me just reduce my screen. Or wait. Yeah, so let's just start now. Right, so I'm going to start with exercise 17.3. 17.1 and 17.2, it's pretty much solvable, right? So I'm going to deal with 17.7 and I'll move on to all of the exercises from here on, right? So I've written two theorems before starting with with exercise 17.3, right? So I've written down theorem 17.3. Theorem 17.3 is the extreme value theorem, which says that if f is a continuous function, wait, let me just highlight this, right? If f is a continuous function, f should be a continuous function over a closed bounded set, S in Rn, right? So Rn means n-dimensional vector, right? Over a closed bounded set S and Rn, right? Then there exists both a maximum and a minimum point, right? So if my set S is n-dimensional, right, and it takes all real numbers, so my maximum point and my minimum point will also be an n-dimensional vector, right? If for example set S is in for example, if set S is in R1, right, or for example I would say it's just in Rn, it's just in R, so n is equal to 1. So this will mean that this is a single variable set, right? So my point C will be just C and D will be just D, right? And C, for example, then let me complete this statement, then I will explain this to you, right? So then there exists both a maximum C, which is an n-dimensional vector again, and a minimum point D in S, that is there exists C and D in S such that, right, such that this fx, the value of fx lies between fd and fc, right? So basically the theorem says that if f is a continuous function over a closed bounded set S and Rn, then there exists both a maximum and a minimum point in S, that is there exists C and D in S such that fx lies between fd and fc. So if a set is closed and bounded and the function given to me is continuous, then in that set I would always achieve a maximum and a minimum, right, over that set. So for example, n is 1 here, right? Here n is 1. Here n is 1. We are dealing with single variable function, right? So here n is 1, single variable function, right? Here. So I would say if n is 1, S belongs to R, S belongs to R, S belongs to R, right? So C and D are 2 points lying in S. So C and D belongs to S and S belongs to R. So I would say for all x, I would just say for all x belonging to S, there exist C comma D such that f of x always lies between f of d and f of c, where c and d are the max and min points respectively, right? I'm just writing this in the rough. I'm going to remove this, right? So if this is a single variable function and c is the maximum point and d is the minimum point, so fx for all x lying between c and d, uh, for all x lying between for all x belong to s, fx will always lie between fd and fc, right? So don't assume c and d to be the endpoints of the interval, right? C and d are not the endpoints of the set. So let me just show you guys one example only. So if for example I have a set S and S is equal to 0 to 1, right? Or let me just take it as -1 to 1. S is -1 to 1. So let's just assume the max occurs at x is equal to half, and min occurs at x is equal to minus half, right? So what this means is, and also f is a continuous function, right? So what this means is, for all x lying between, for all x belongs to s, for all x belongs to s, which implies for all x belongs to and s is equal to -1 to 1, so for all x belong to -1 to 1, we always have the value of f of x lying between f of minus half and f of half, where max occurs at x is equal to half and min occurs at x is equal to minus half. This is what we mean when we take n is equal to 1. So the set becomes a one-dimensional vector, right? So now let me just remove this, or let me just let it be there only, right? So theorem 17.4. Now the necessary first order condition, theorem 17.4 says that let f be defined in a set S and Rn, and let C, again the n-dimensional vector, be an interior point in S at which f is differentiable. Interior point in S at which f is differentiable. A necessary condition for C to be a maximum or a minimum point for f is that C is a stationary point for f. That is, f dash C is equal to 0. So what this means is, now the necessary first order condition, right? So let f be defined in a set S and Rn. F be defined in a set S and Rn. I have explained this, what S in Rn means. N is a so for example I have n is equal to 2. If I have n is equal to 2, so n is equal to 2 means S belongs to R square, which means S will have a function f, and the function f may have a form like, or not may, will have a form like f x comma y, right? So it will become a two-dimensional function, right? So if I would write s is equal to, -1 to 1, I would say f of x comma y belongs to, or I would say f of x comma y is a continuous function, and f of, now if x is for example half, I would say y is equal to 0, right? So f of half comma 0 is a max, and f of minus half comma 0 is a min. Then I would say fx comma y always lies between f of minus half comma 0 and f of half comma 0, right? So basically it will be a two-dimensional function when we say r square, right? Now let me just remove this. Now coming back to the statement, necessary first order condition. This says that let f be defined in a set S and Rn, and let C be a n-dimensional vector, or C be a point, be an interior point in S at which f is differentiable. A necessary condition for C to be a maximum or a minimum point for f is that C is a stationary point of f. Now this is a necessary condition, not a sufficient condition. There is a difference between necessary condition and a sufficient condition, right? But let me just explain you what this statement means. Let's just say C belongs to R only. So C, we have a point C, and we are saying that C is in the interior of S. So it is not a boundary point. You know the difference between a boundary point and a non-boundary point, right? So if I have S belongs to my S equals to -1, 1, so this -1 and this 1 both will be the corner points, right? And all the points inside this line will be the interior points. So if f is a set, so be interior point in S, right? So so any x, so if I say that S is equal to -1 to 1, so I would say any point x which is not equal to -1 to 1 but lies in between -1 and 1 is an interior point. I don't know why I am explaining all of this. I should have just moved on to the questions, but yeah, this will give you a lot of conceptual clarity. So x lies between -1 to 1, so x is a interior point, and if x is equal to -1, 1, we say that x is a corner point, right? So x becomes a corner point. Then x is a corner point slash a boundary point. Now S can also become two-dimensional. They can give us S is equal to x square plus y square less than equal to 1. Then what does this mean? That x belongs to -1 to 1 and y belongs to comma y belongs to -1 to 1. So this becomes a two-dimensional set, right? This becomes a two-dimensional set. So S belongs to R square here, right? So this becomes a circle. So this circle becomes, so this circle, we have a circle here in this case. Why am I not able to draw a circle, right? So this becomes a circle here, and this is -1, for example. This is 1, this is 1, and this is -1, right? So all the points lying on the circumference or on the circle, so x square plus y square is equal to 1 are the boundary points. And all points less than 1 are the interior points. So the necessary condition, I hope you guys can see this. So -1 to 1 is an interior point. X is equal to -1, 1. Then x is a corner point, boundary point, right? So if I just zoom this out, I hope you guys can see. Right. So I'm trying to write bigger now. I'll try to write in larger font from now on. I don't think you guys were able to see earlier, right? So x square plus y square is equal to 1 are the boundary points, and x square plus y square less than 1 are the interior points, right? So now the condition says to qualify for C, which is an interior point, to qualify C as an interior, as a maximum or a minimum, and C being an interior point, has to be a point at which f is differentiable, and the C point should also be a stationary point. Now, what does stationary point means? Stationary point just means that what is meant by stationary point is the derivative at this point should be equal to 0, right? So f dash c should be 0. So they are saying that if c is a interior point at which f is differentiable, otherwise we won't be having a stationary point. So they are saying that let f be defined in a set S and Rn, and let C be a interior point in S at which f is differentiable, a necessary condition for C. Now the necessary condition comes. So first of all they are saying let f be defined in a set S and Rn, C is an interior point. I have explained what is an interior point at which f is differentiable. If it is not differentiable, then it is not a question. Then there is no, then we can't say anything because it is not differentiable at all. So when a point is not differentiable, it can be a critical point, but it cannot be a stationary point, right? So then we come, and the necessary condition then says that the necessary condition then says, after you have qualified all of this, the necessary condition now comes in and says that a necessary condition for C to be a maximum or a minimum point, for us to even think for it to be a maximum or a minimum point for f, is that C is a stationary point for f, that is f dash C is equal to 0. Now this is a necessary condition, not a sufficient condition. A sufficient condition tells us that yeah, you can be satisfied with this condition. If this condition gets satisfied, it is sufficient to prove that we have a maximum or a minimum, and we can just close our eyes and take a large and calm breath and can say that oof, this question is finished now and we can move ahead. But now the necessary condition says that I am necessary, not sufficient. I have to be met, but I am not giving you any guarantee that meeting me will give you what is required, right? So you have to meet me, you have to make me feel satisfied, but I am not guaranteeing you that I will make you feel satisfied. So necessary condition is basically saying that if, for example, the point C works out to be the maximum or a minimum, then these conditions would have automatically been met, right? So a necessary condition for C to be a maximum or a minimum point for f is that C is a stationary point for f, that is f dash C is equal to 0. So if we have any point which is lying in a set S in Rn, and C is an interior point in S at which f is differentiable, and that C turns out to be a stationary point, then we can write it aside and say it can be a maximum or a minimum. Then we would have to check if there are other stationary points also. Then we would have to check at the boundary point also, right? So this, for example, here we would have to check at f of minus 1. We would have to check f of minus 1 and f of 1. So here we would have to check all points satisfying this x square plus y square is equal to 1. This circumference point, we would have to find these edge points, right? And then we would have to compare that to the functional value at C, which is f of C, right? And then we would compare that to C, and we would check which is greater or larger. It might be that the stationary point or the interior stationary point is not at all a maximum or a minimum. At times it will happen, and we get both our maximum and minimum from the boundary points, right? So now let's just move ahead and solve questions. I'm not going to take any examples. I need some water. Let me just come back. Right. Right. So let's start with the question. They've also written a proper way or a method on how to solve the questions coming in the upcoming exercise. Let me just read that out. The problem that will be given to you will be find the maximum and a minimum value of a differentiable function fx defined on a closed bounded set S and Rn. The solution, the first point says that find all stationary points of f in the interior of S. Let's just write this. Find all stationary points. So our method of solving will be method will be find all stationary points. Find all stationary points find all stationary points find all stationary points. Second will be find the largest and the smallest value of fx on the boundary of f of S. So S is a set, right? Closed and bounded set. And what does closed and bounded means? If we have a set like this, is this closed and bounded? No. This is bounded but not closed. This is bounded, not closed. This is again bounded but not closed on both sides, so it is not closed. Bounded but not closed. And this is both bounded and closed, right? So we will say that this is bounded and closed. So now moving on, find all stationary points in the interior of S. In the interior of S, second point says that find the largest and the smallest value of fx on the boundary of S. So largest and smallest values of f of x on the boundary on the boundary. Compute the values of the function at all points found in 1 or 2. The largest functional value in 3 is the maximum, right? So now after doing both of these steps, we'll just compare the functional values and find which is the maximum or the minimum. So now let's just start. Let me just see the pen that I'm taking. So we have been given an example 17.5. 17.6 is a very important example, but you have to do that on your own. Now I have problem 1, problem 2, problem 3, 4, 5, 6, and so on. In each exercises there are some harder problems which I feel some of the harder problems you should solve, but some other harder problems I think that sometimes they go beyond the scope of this book and require a lot of creativity to solve. So I would be seeing which harder problems I would tackle along this process. I don't know why my light is dimming. I hope you guys can see me. Right, so I'm going to take up question 1 or question 1. Let's just start with question 1 here. So question 1 says that problems 17.3. So the question 1 says that, let me just zoom in. So question 1 says that f x comma y, which is equal to 4x minus 2x square minus 2y square, right? So this is the function given to us, and s is the set which is x comma y, x square plus y square less than equal to 25. So let's just find the stationary point. For finding the stationary point, we would just find the partial derivative of the function. So this is del f by del x, right? So the partial derivative of x equated to 0, partial derivative of y equated to 0, right? So 4 minus 4 of x is equal to 0. Now del f by del y, which is f of y, equals minus 4y, which is equal to 0. So y is equal to 0 and x is equal to 1. So the point that I have, my stationary point, my interior stationary point becomes 1 comma 0. Also, is this an interior stationary point? Should we check? If I put this point in this constraint or the set given to me, so 1 plus 0 is equal to 1, which is less than 25. So yes, this is an interior stationary point. So now let me just rub this. This is not needed. There are one or two questions where you find the stationary point and it comes out to be lying outside of the set. Right. So yeah. Now we have a point 1 comma 0. Now we need to check for the boundary point. How do we do that? What I can do is I'll just put in the constraint in the function and I'll find the point, right? So my function f x comma y, which is 4x minus 2, I'll be taking common, minus 2, so x square plus y square, and x square plus y square is given to me as 25, right? So fx comma y just becomes g of x. After putting in this value, this becomes 2 into 25. 4x minus 50. If I just find the derivative of g of x, which is g of x was f of x comma, so I can say in place of, or I just write this was the same function. What I did was I just substituted the constraint. So I just substituted the constraint in this function and this became g of x. This became g of x, right? So if I find the derivative of g of x with respect to x, I find the derivative to be 4, right? And derivative 4 says that g is an increasing function. So g will give me the maximum value when I put in the highest value of x, subject to my constraint, which was x square plus y square equal to 25, right? So subject to this, the maximum value that x can attain is x lies between minus 5 and 5. So g of 5 is the maximum value, is the max here, subject to this function for g of x. G of 5 is the max and g of minus 5 is the min. And when x will be 5, when x is 5, y will become 0. When x is equal to minus 5, y will become 0. So we have another set of points, another set of 2 points, which is, so the next set of points that we have is, the next set of points that we have is the next set of points that I have is f of f of 5 comma 0, which is 4 into 5 minus 50. So this is 20 minus 50 minus 30, and f into minus 5 comma 0, which is 4 into minus 5 minus 50, which is equal to minus 20 minus 5 minus 70, right? And here my f1, so 1 comma 0 was the interior stationary point, so f1 comma 0 comes out to be, so 4 minus 2 minus 0, so this becomes 2. So seeing the value of f1 comma 0, f1 comma 0, f5 comma 0 and f minus 5 comma 0, I can say that my max occurs at 1 comma 0, which is f of 1 comma 0 equal to 2, and min at minus 5 comma 0, f of minus 5 comma 0, which was equal to minus 70. Right, so this was the whole process of solving this question. Let's just take up one more question. I was going to end the video, but let's just move on and take one more question. Let me just check the answer to this question. Yeah, what you have did, what I've just done is absolutely correct. So now I've covered part A and part B also of the first question. You can just see. Right, so let's just move on. Second question part A is a bit different. It will excite you. So f I don't know how much charging my Apple Pencil has. So f of x comma y is x cube plus y cube minus 9xy plus 27, subject to x lying between 0 and 4, subject to right, so this is my function and this is the constraint given to me. So now finding let's just now find the interior stationary point first. So f of x, which is the first partial derivative of f with respect to x, gives me 3x square minus 9y, and f of y gives me 3y square minus 9x, 0. So this gives me 3x square is equal to 9y. This gives me 3y square is equal to 9x, which is x square is equal to 3y, which is y square is equal to 3x. So if I just use this condition and this condition, so this is first, this is second. So x square is equal to 3y. So x square by 3 is equal to y, and y square is equal to 3x. So x square by 3 whole square is equal to 3x. So x to the power 4 by 9 is equal to 3x. So if I just take this to the other side, If I just take this to the other side, this gives me x4 is equal to 27x. So x4 minus 27x is equal to 0. So if I just take x to be common, this gives me x cube minus 27, which is equal to 0. So from here I have 2 points, x is equal to 0 and x is equal to 3, right? So now my y is x square by 3. This implies that y is equal to 0 comma 3. So 3 square is 9 and 9 upon 3 is 3. So I have 2 points, 0 comma 0 comma 3 comma 3. Now let me just check if these are the interior stationary points. Interior stationary points. Interior stationary points. I hope you guys get the idea. So interior stationary points. So let me just check. My x lies between 0 and 4. My y lies between 0 and 4. Both of these points are interior points. Now let me just move on and check for the boundary points. Now what does my boundary say? My boundary says that my x should lie between 0 and 4. My y should lie between 0 and 4. So this means that if I just zoom in now here, just watch. This means that if I just draw a graph, so this is the y-axis, this is the x-axis. This means that this is the 0, so my x lies between 0 and 4 and my y lies between 0 and 4, right? So now I'm going to take, these are 4 constraints, so 4 edges. First edge, second edge, third edge, fourth edge, 4 edges, right? So now what I'm going to do is I'm going to substitute them one by one. At the first edge, I have all those points where x lies between 0, 4, y belongs to y is equal to 0. Y is equal to 0. At all the points lying on the first edge, on this edge, I have all those points where x lies between 0 and 4 and y is equal to 0. Similarly, on the fourth edge, I have all those points where y lies between 0 and 4 included, and x is equal to 0. On all points on the second edge, I have y lying between 0 and 4 and x equals to 4. X is equal to 4. On all points lying on the third edge, I have x lying between 0 and 4 but y being equal to 4. So you can see here, right? So now let me just use my eraser. So I have to write 4 cases now. I'll just be using this graph again and again. So for case 1, I am just going to solve case 1, case 2, case 3. So case 1, x belongs to 0, 4, right? So x belongs to 0, 4. This is the case 1. So f of x, y, So I would be saying that this becomes, on first edge, this fx comma y becomes f of x comma 0 and y is equal to 0 here, right, on the first edge. First edge, this edge, right? So if I just put in 0 in place of y and x, let x be in place of x only, so my function becomes x cube plus 0, x cube plus 0 minus 0 plus 27, so x cube plus 27. So this becomes x cube plus 27, right? X cube plus 27. If I could just show you the function again, so x cube plus 27. I hope you guys saw it. So x cube plus 27. So this, I would be writing this as g of x. This becomes x cube plus 27. So g dash x, this is equal to 3x square plus 27 plus 0 and 3x square. 3x square means that this is an increasing function. So the first derivative, the derivative is positive. So this is an increasing function. Increasing function tells me that as I increase the value of x, the function value increases, right? So g of 4 will be the maximum value on the first edge, and g of on the first edge, right? So remember this, on the first edge, not overall, just on the first edge. So g of 4 is the maximum value on the first edge, and g of 0 is the minimum value. So g of 0 means f of 0 comma 0. G of 4 means f of 4 comma 0. So f of 4 comma 0 turns out to be f of 4 comma 0 turns out to be, so this was my x. So 4 cube is 64 plus 27. So 64 plus 27 is 84, 91, and f of 0 comma 0 is 27. So if I just put in 0 in place of here, 27. So this is, I have two values here, right? Two different values here. So now what I can do is case 2. So I would have to go on h2. So case 2. Case 2 is edge 2. So on edge 2 I have, or let me just take edge 4 first. No, let us take edge 2 only. Edge 2. At edge 2 I have x is equal to 4 and y lying between 0 and 4. X is equal to 4, y belongs to 0 comma 4, right? So f of y comma 4. So if my x is 4, what am I doing? So this is 4 and this is y, right? So 4 comma y. So here x is 4 and y is lying between 0 and 4. So if I just go to my function, this gives me x cube is 64 plus y cube minus 9 into 4, 36y plus 27. So 64 plus 27 becomes 91 plus y cube minus 36y. So this becomes 91 plus y cube, minus 36 by 91 27 plus 27 plus 36, 91 plus y cube minus 36y. 19, right. So I can write this function as h of y. So h of y comes out to be 91 plus y cube minus 36y. So h dash y becomes 3y square minus 36. So now I don't know if this is an increasing function or not. So I'll be just putting in 0 and be checking the points where this is an increasing function or decreasing function, right? So 3y square minus 36, this implies y square minus 12 is equal to 0. 3 into 12 is 12. So y square is equal to 12, y is equal to y square is equal to 12, then root of y will be 4 into 3, so 2 plus minus 2 root 3. But I would be only taking y is equal to 2 root 3. Why? Here I have y plus minus 2 root 3. Here I have y is equal to plus minus 2 root 3. But I would only be taking y is equal to 2 root 3. There's the reason why. The reason is my y and x both lie between 0 and 4. So why would I be taking a negative value, right? So I'd be rejecting one value. So y is equal to minus 2 root 3 is rejected as my y lies between 0 and 4. Between 0 and 4. So 2 root 3. 2 root 3, right? So 2 root 3 is my value. So this means that I would have 2 root 3, but for drawing the critical value I can write, no? Just for finding the critical points I can write minus 2 root 3, but the value is rejected, right? But for showing where the function is increasing or decreasing, I am just writing that. So positive, negative, positive. Now you can put in points and check if the first derivative is coming out to be positive or negative. But yeah, so at all points greater than 2 root 3 I have an increasing function. At all points lying between minus 2 root 3 and 2 root 3 I have a decreasing function, but minus 2 root 3 is rejected. So if I just draw 0 also, if I just write a 0 here also, then also I can say that, or let me just remove this 0. Let me just remove this 0 here, for example. Right, so my 2 root 3 is rejected, but I have 0 which is less than positive 2 root 3, and any point lying between 0 and 2 root 3 is also giving me a decreasing function. So I can say that between 0 comma 2 root 3 h dash y is less than 0, 2 root 3 to 4, because 4 is my upper bound, h dash y is greater than 0, right? Greater than, less than equal to 0 and greater than equal to 0, right? So my points that I would have to check will be, so you can see that local min will occur at 2 root 3. I don't want to use the term local min, but 2 root 3 is an important point for us, and 0 is an important point for us, and 4 is an important point for us. This means that we would be checking h of 0. H of 0 is 91. H of 4 will be 91 plus 64 minus 36 into 4. So 36 into 4 is 64. So 36, no, 36 into 4 is not 64. 4, 3, 124, 4 and 6, 24, 144. So 91 plus 64 is 95, 160, 155. Yes, 155 minus 144, which is 11. 11. So this turns out to be 11. So h of 0 is 91, h of 4 is 11, and h of 2 root 3 is 91 plus 2 root 3 whole cube minus 36 into 2 root 3. So 91 and 2 root 3 whole cube is 2 cube is 8, and 3 square is 3, root 3 square is 3, so 8 into 3, 24 root 3, so 24. So this becomes 24 root 3 minus 72 root 3. So let me just use this gives me 91 plus 48 root 3. If I take an approximate value here of h of 2 root 3, root 3 is 1.73, but if I take an approximate value and take root 3 as being approximated to 1, which is quite wrong, but I'm just taking an approximate value, so this will give me 91 plus 48, which is an approximate value 130, 139 is an approximate value. But one thing is h of 0 is h of 0 which was 91 is equal to f of 4 comma 0 which was 91. h of 4 was f of 4 comma 4 which was 11, and h of 2 root 3 is f of 4 comma 2 root 3, which is equal to 1 approximately equal to or 91 equal to 91 plus 48 root 3 approx is 139. So solve case 1 and case 2. Now we can see that this is a symmetric function. So x cube plus y cube minus 9xy plus 27. Right? This is a very symmetric function. Right? So if I just find case 3 and case 4 also, I would be getting the same values only, right? But what I'll be doing is I'll be showing you some part of it. So let me just solve case 3 and case 4 here. So this is starting from this. Here is case 3 is h3 is h3 becomes x lying between 0 and 4 and y is 4. So when y is 4, x belongs to 0 comma 4, my function f of x comma 4, which again becomes 91, again becomes x cube plus 64 minus 36x plus 27, so this becomes 91 plus x cube minus 36x this time, right? So this is again a symmetric function. So if I just give this a name as m of x, m of m is 91 plus x cube minus 36x, so m dash x is again 3x square minus 36, which is equal to 0. So again I would take 3 common, x square minus 12, x is equal to plus minus 2 root 3, reject negative 2 root 3, but while creating or finding the points where the first derivative is changing signs, just use that. So use this point 2 root 3 and 2 root 3, so this becomes positive, negative, positive. So m dash x is less than equal to 0 for all x belongs to 0 comma 2 root 3, and m dash x is greater than equal to 0 for all x belongs to 2 root 3 comma 4. The same thing that I wrote just here, right? This and this. So again the points will turn out to be m of 2 root 3, m of 0, and m of 4 comma 4, sorry, m of 4. M of 4, which are again equal to the same process. So again the values will come out to be 2 root 3 comma 4, f of 0 comma 4 and f of 4 comma 4. So f of 4 comma 4 was f of 4 comma 4 was 11. So 11, this will be 11 and this will be approximately 139 approx, right? So case 4 will again give me same solutions as case 1, because here my y is lying between 0 and 4 and x is 0. So again my function will become symmetrical to this, and again I would have two values here in case 4. If I just write here case 4, so if I just use a dotted line here, so if I just use a dotted line here, my case 4 will become x0 y belongs to 0 comma 4, and in the end I would have value as 0 comma 0 is equal to what? 0 comma 0 gives me 27, right? So 27 and f of 0 comma 4 will give me 90. So this will be my values. Now comparing them, now in the end when I have to find my answer, the max or minimum values, my stationary points were 0 and 0 0 and 3 comma 3. So at my stationary points, the video has become 1 hour long. So 0 comma 0 becomes f of 0 comma 0 becomes 27, f of 3 comma 3 becomes 3 cube 27 minus 9 into 9 is 81. So 27 into 3, 27 is 0. F of 3 comma 3 is 0, and f of so the largest point or the least point, I am going to just write this. The least point from here becomes this 11, and the largest point becomes this 4 comma 2 root 3, and from there also. So right, so I'm just writing those 2 points only, I'm not writing the other points. So 4 comma 4 is equal to 11, and f of 4 comma 2 root 3 is equal to f of 2 root 3 comma 4, f of 4 comma 0 is 91. F of 4 comma 2 root 3 and f of 4 comma 4, and similarly from there also 2 root 3 and s. So this becomes here. So this becomes 91 plus 48 root 3. Approx I am taking 139. So this will be the max values at 4 comma 2 root 3 and 2 root 3 comma 4, min at 3 comma 3, right? So if I just check my answer, second question, part A. Oh, I don't have the solution to this. I would have to check my even problems. Let me share my screen with you. Let me just open this. I just want to show you guys that what we're doing is real. So I hope you guys are getting my handwriting, otherwise there won't be any point. Yes. So if I just present my screen, window capture, I'm so sorry for this. I don't know what has happened. I hope you guys can watch my screen now. Right. So returning to my PDF, you can see that the second question part is the only stationary point is 3 comma 3 and 0 comma 0 is a stationary point of the boundary of S. Along the four parts of the boundary we find f0 comma 0, 4 comma 0, 4 comma root 12, root 12 2 root 3, 4 comma 4, 2 root 3 comma 4 and 0 comma 4. Comparing the values of f at all these points, we find the f as minimum 91 at 0 comma 4, at 4 comma 0, minimum 0 at 3 comma 3. So this is incorrect. Just see to it. The minimum is not 91. They might be saying that the maximum is 91, right? But yeah, the minimum is 0. Minimum is 0 at 3 comma 3, and they are saying that the maximum is, let me just see, find the maximum and the minimum point defined for S, but let me just see. Returning to our solution, returning to our solution, returning to our solution. Returning to our solution. If I put 4 comma 2 root 3, so is 2 root 3 so yeah, let me just show you guys something. So is 2 root 3 2 into 1.73, this shouldn't be greater than 4, right? So 1.73, if I just multiply with this with 2, 2 3s are 6, 2 7s are 14, 2 1s are 2 and 3 point and this, yeah, so 3.46, yeah, this is less than 4, yeah. So they have missed this point, but the maximum should occur at 4 comma 2 root 3, 2 root 3 comma 4, and the minimum should occur at 3 comma 3, which is 0. You can just check also by putting in the values. So this 4, if I just put in 4, this gives me 64, and this gives me 2 root 3, so 2 root 3 cube is 2, the cube of 2 root 3 will be 2 cube is 8, and then this will become 3 root 3, right? So root 3 into root 3 and 3, so this becomes 24 root 3, right? And this is minus 9 into 2 root 3, and this y is, minus, this is 2 root 3, and x is, and x was x was 4, so this is 72 root 3, 72 root 3, 72 root 3, 9 to 4 30, 72 root 3, yes, plus 27, so 64, 64 plus 27 becomes 91, and 72 root 3, this was negative 72 root 3, and this is positive, so this becomes negative 48 root 3, negative 48 root 3. Yeah. Yeah, so what they have done is actually correct, and what I have done was a bit wrong. I wouldn't be removing this from the video though, right? So certain times you make silly errors. We did all this just to mark the answer incorrect, and I'm so sorry for that. So if I just take this root 3 as 1, so this will give me 98 minus 48, 98 minus 40, so 51, 51 minus 8, 51 minus 50 minus 8, 42, 43, approximately 43 approx. If I just add this also, 43 plus 40, 88, 91, yes. So approx is 43, approx is 43. So yeah, the max at max at 4 comma 0, max at 4 comma 0, 0 comma 4, yes. So this is the max and this is the min. Or if I just correct this in my notes, please correct this. At the end I have made a certain error in a certain error here, right? So my value should come out to be here it should be negative. So it should be negative, so this should have been negative. So I'm so sorry for the error at the end, right? And I'm going to end the video now. It's 1 hour 6 minutes, and I'm not going to remove this from the video. If you have any doubts or if you have any suggestions for me to improve this video, I would love to take them, right? So this is a very new topic for me, new topic to explain to you guys, otherwise not a new topic for me, right? So I hope to see you guys in the next video, and I hope you guys like the video. If you like the video, do share the video and put in a comment. It encourages me to put in regularly more videos. I wasn't very regular since the past 1 month, but now I'm going to try to come back on track and try to upload one video each week, right? So thank you, and I hope to see you in the next video. Bye bye. One more thing, I'm going to share the PDF in the description also. I'm going to try and put it in, and I've made the correction also, right? So if you want to go and look up the solution, right? So you are free to do that. Thank you.